What if everything we think we know about the universe's fundamental rules is just the tip of the cosmic iceberg? Picture this. Deep in the void of space, far beyond the reach of our telescopes, the laws of thermodynamics, those bedrock principles that govern energy, heat, and even the arrow of time, might not behave the way we've always assumed. Entropy, the silent architect of chaos, could be weaving a hidden tapestry across the cosmos, shaping everything from the birth of galaxies to the enigmatic dance of black holes. This isn't just a theoretical curiosity, it's a revelation that could rewrite our understanding of reality itself. Think about the last time you watched a cup of coffee cool or saw a shattered glass that could never reassemble itself. These everyday moments are ruled by entropy, the universe's relentless push toward disorder. But what if, in the vast emptiness between stars, entropy isn't just a destroyer? What if it's a cosmic sculptor, quietly guiding the formation of structures we're only beginning to comprehend? From the swirling arms of distant galaxies to the unfathomable depths of black holes, entropy might hold secrets that challenge the very foundations of physics. And here's the kicker. If we're wrong about how entropy works in deep space, we might be wrong about the ultimate fate of the universe. This journey isn't just for physicists or astronomers. It's for anyone who's ever looked up at the night sky and wondered how it all works. Together, we'll unravel the mysteries of entropy's cosmic role, exploring how it could redefine everything from the stars to the fabric of spacetime. We'll venture into the heart of black holes, where the rules of thermodynamics might bend beyond recognition, and peer into the distant future of the cosmos, where entropy could have the final say. By the end, you'll see the universe in a whole new light, one where chaos isn't just inevitable but essential. So buckle up. We're about to question everything: heat, energy, and the inevitable march toward disorder. These are the pillars of thermodynamics, the universal rulebook that shapes everything from steam engines to supernovas. Let's start with the basics. The first law is simple: energy can't be created or destroyed, only transformed. It's the cosmic accountant, ensuring the universe's ledger always balances. The second law introduces entropy, the measure of chaos, stating that in any closed system, disorder always increases over time. Think of it like a deck of cards: shuffle it once and it's neatly ordered, shuffle it 1,000 times and it's pure randomness. That's entropy at work. Then there's the third law, which tells us that as temperatures approach absolute zero, entropy theoretically hits a minimum, a frozen whisper of order in the cold dark. These laws seem absolute, dictating everything from why ice melts to why stars burn out. But here, where it gets wild, what if the vast, alien landscapes of deep space don't play by the same rules? In the crushing gravity near a black hole or the searing plasma of a quasar, entropy might not just increase, it could twist, warp, or even reverse. Picture a river flowing uphill. That's the kind of paradox we're staring down. And if entropy behaves differently in the cosmos's extreme environments, it could mean our understanding of reality is built on sand. The second law isn't just a guideline, it's the heartbeat of time itself. So what happens when that heartbeat skips? The answer could rewrite physics. Here on Earth, entropy feels like an old friend, one that constantly rearranges our world in ways we barely notice until it's too late. Watch an ice cube melt in your drink, and you're seeing entropy in action. The rigid, orderly structure of ice surrenders to the chaos of liquid water, molecules jostling freely as heat energy disperses. Or take a crumbling on the beach. What was once a carefully sculpted fortress becomes a shapeless mound, grains scattering irreversibly in the wind. Even our own bodies are for entropy. Every cell division, every chemical reaction in our muscles, every fleeting thought sends tiny ripples of disorder through our biology, inching us inevitably toward decay. These aren't failures. They're the universe ticking along as prescribed by the second law. But here's the twist: Earth isn't a closed system. Sunlight floods in daily, pumping energy into every leaf, ocean current, and weather pattern. This constant influx lets pockets of order emerge temporarily. A seed becomes a towering tree, defying chaos by drawing energy from its environment. A refrigerator cools your food, not by breaking the laws of thermodynamics, but by exporting heat elsewhere. These open systems create local oases of order, like eddies in a rushing river. Yet the river always wins. However complex or enduring these structures seem, they're just delaying the inevitable. The tree will fall, the fridge will break, the star that gives us light will burn out. Now zoom out to the cosmic scale. Space isn't just vast, it's teeming with energy flows that make Earth's open systems look trivial. Black holes devour matter and spit out jets of plasma. Nebulas churn with enough raw material to birth stars for billions of years. Could these extreme environments bend entropy's rules or even rewrite them? Imagine a galaxy where gravity's grip is so relentless that disorder doesn't just increase, it folds back on itself, like a wave crashing into the shore only to retreat and gather strength anew. If entropy behaves differently where energy densities dwarf anything in our solar system, we might be missing a fundamental chapter in physics. The coffee cools, the glass shatters, but in the heart of a quasar, could the reverse be true? Now consider this cosmic paradox. While entropy dictates that disorder must rise, the universe keeps assembling galaxies like clockwork. These sprawling cities of stars, bound by gravity, should be impossible under strict interpretations of the second law. Gravity defies expectations by pulling matter into ordered structures, spiral arms, clusters, superclusters, as if entropy's relentless march were being hijacked. Even stranger are black holes, the ultimate paradox. They devour matter, increasing entropy in their vicinity, yet their event horizons hide secrets. Some theorists argue that inside a black hole, entropy might not just stall, it could reverse, like a shattered glass reassembling itself in reverse motion. Then there's dark energy, the invisible force accelerating the universe's expansion. As space stretches, matter spreads thinner, which should maximize entropy. But what if dark energy isn't just dispersing chaos? Recent simulations suggest it might be sculpting hidden order on scales we can't yet measure. Imagine a vast cosmic loom, weaving patterns in the void where entropy's rules soften. Studies of distant quasars reveal pockets where energy flows resemble refrigerators, localized regions where heat seems to move backward, chilling instead of warming. These anomalies aren't glitches, they're clues. The implications shake physics to its core. If entropy can decrease in extreme environments, it means the second law isn't universal, just a local guideline for tame places like Earth. Some researchers propose that spacetime itself might have entropy gradients, like valleys where chaos pools and peaks where order clings. Others speculate that dark matter could be interacting with entropy in ways that rewrite the cosmic playbook. The debate is fierce, because if entropy isn't the iron rule we thought, then time, energy, and even the fate of the universe might be up for renegotiation. One thing's certain, the cosmos refuses to be boxed in by textbooks. Every anomaly whispers that we've barely scratched the surface of thermodynamics' true story. And if entropy isn't the villain we imagined, if it's more like a cosmic choreographer, then the universe might be far stranger and far more beautiful than we ever dreamed. Black holes aren't just cosmic vacuum cleaners. They're thermodynamic enigmas that stretch our understanding of entropy to the breaking point. Picture a star collapsing under its own gravity, crushing down to a point so dense that not even light can escape. At the surface of this abyss, the event horizon, something bizarre happens to entropy. In classical physics, entropy always increases, but here it's as if the rulebook gets tossed into the void. The matter falling in doesn't just vanish, its information, the blueprint of its order, seems to be erased, which should send entropy skyrocketing. Yet somehow, black holes also radiate energy, slowly leaking particles back into the universe through a process called Hawking radiation. This glow, predicted by Stephen Hawking, is where things get truly mind-bending. Quantum mechanics tells us that empty space isn't really empty. It's a seething foam of virtual particles popping in and out of existence. Near a black hole's event horizon, some of these particles get torn apart, with one falling in and the other escaping as real radiation. Here's the kicker. This escaping energy carries entropy with it, as if the black hole is sweating out disorder. Over unimaginable eons, this drip feed of radiation could cause the black hole to evaporate entirely, leaving behind only a whisper of its original chaos. But if that's true, where does all the swallowed entropy go? Does it vanish, or is it somehow encoded in the radiation itself? The math suggests something even stranger. Black holes might have the maximum possible entropy for their size, meaning they're not just chaotic, but the most efficient entropy factories in existence. A single black hole could contain more disorder than all the stars, planets, and dust in a galaxy combined. And yet, their radiation hints that entropy isn't trapped inside forever. It's being slowly released, like a cosmic pressure valve. This creates a paradox. If black holes both consume entropy and radiate it away, are they upholding the second law or rewriting it? Some theories suggest that the event horizon acts like a one-way mirror, hiding entropy's true behavior in ways we can't yet observe. Others propose that black holes are stitching entropy into the fabric of spacetime itself, weaving it into the universe's hidden dimensions. What's clear is that black holes don't play by the rules we're used to. They're not just exceptions to thermodynamics. They might be showing us where our current laws break down entirely. If entropy can leak out of a black hole, what else is possible? Could there be regions of the universe where disorder doesn't just increase, it fluctuates, reverses, or even resets? The answers could redefine not just black holes, but the fate of everything. Dark energy might be the universe's greatest unsolved mystery, an invisible force stretching space itself apart, pushing galaxies away from each other faster and faster against the pull of gravity. But what if this cosmic acceleration isn't just some exotic, unknown substance? What if it's deeply tied to entropy, the very fabric of disorder we've been exploring? Picture the universe as an inflating balloon, its surface speckled with galaxies. As it expands, the space between those galaxies grows, and with it, the total entropy of the cosmos. Some physicists argue that dark energy isn't a separate force at all. It could be the thermodynamic echo of this ever-increasing chaos, a side effect of the universe's relentless slide toward disorder. Think of it like a stretched rubber band. The more you pull, the more energy builds up in the tension, except in this case, the rubber band is spacetime and the energy is dark energy. The startling idea here is that entropy might not just be a passenger on this cosmic ride, it could be the engine. Every bit of space that's created by expansion carries its own tiny dose of entropy, and collectively, these fragments might be fueling dark energy's push. It's as if the universe's disorder isn't just a consequence of expansion, it's actively driving it. But there's a twist. If dark energy were purely an entropy effect, we'd expect its strength to change as the universe evolves. Yet observations suggest it remained eerily constant over billions of years, like a steady hand on the cosmic throttle. This has led to wilder theories that dark energy isn't just linked to entropy but could be something even more profound. A shadow of extra dimensions, a quantum fluke frozen into the vacuum of space, or even a sign that our universe is just one bubble in a vast multiverse. The stakes couldn't be higher. If dark energy truly is entropy in disguise, it would mean the fate of the cosmos, whether it rips apart, cools into darkness, or cycles into something new, is written in the language of thermodynamics. But if it's something else entirely, we might need to rethink not just dark energy, but the very nature of reality. One thing's certain, the deeper we dig, the clearer it becomes that entropy isn't just a footnote in physics. It could be the hidden force shaping everything. What if the universe isn't three-dimensional at all, but a vast cosmic hologram? The holographic principle flips our understanding of reality upside down, suggesting everything we see, stars, galaxies, even the fabric of spacetime, might just be a projection of information encoded on a distant, two-dimensional surface. This isn't science fiction. It's a serious theory born from the study of black holes. When matter falls into a black hole, its information doesn't vanish. It gets smeared across the event horizon like ink on a stretched sheet of paper. And if that's true for black holes, why not for the entire universe? Here, where entropy enters the picture. If the universe is a hologram, then entropy, the measure of chaos we've been tracking, might not be a fundamental force at all. Instead, it could be a shadow, a side effect of how information is coded on that hidden 2D surface. Think of it like watching a movie. The explosions, the drama, the emotions, they all seem real, but they're just patterns of light projected from a flat screen. In the same way, entropy's relentless rise could be an illusion, a cosmic sleight of hand where the real action is happening somewhere we can't see. The implications are staggering. If entropy isn't a law but a projection, then thermodynamics as we know it might be more like a user manual for the hologram, not the rules of reality itself. Some physicists argue this could explain why black holes seem to defy entropy's rules, or why dark energy behaves so mysteriously. The holographic universe might have its own, deeper logic, one where disorder isn't inevitable, just a quirk of how information is displayed. Imagine a future where we crack this code. We might discover that entropy can be manipulated, even reversed, by tweaking the universe's underlying data. Far-fetched, maybe. But remember, every great revolution in science began as a heresy. The holographic principle isn't just rewriting thermodynamics, it's inviting us to question whether we've been reading the cosmos all wrong. And if that's true, the real universe could be stranger than anything we've dreamed. Down at the quantum level, the universe doesn't play by the neat, predictable rules we're used to. Instead, it's a seething, chaotic dance where particles flicker into existence for fleeting moments before vanishing again, a phenomenon called quantum fluctuations. These aren't just tiny blips, they're the universe's way of testing its own limits, borrowing energy from nothingness and paying it back almost instantly. But here, where entropy gets interesting. Normally, disorder always increases, yet in these quantum bubbles, something peculiar happens. For the briefest instant, entropy can appear to decrease, as if the universe forgot its own rules. It's like watching a shattered glass spontaneously reassemble itself, only to shatter again before you can blink. This isn't just a microscopic curiosity. Scale it up, and quantum fluctuations could be shaping the cosmos in ways we're only starting to grasp. Take cosmic voids, those vast, empty regions between galaxies where matter is almost non-existent. In these deserts, quantum effects might dominate on scales larger than entire solar systems. Without the interference of matter or radiation, the vacuum itself becomes a playground for fluctuations, potentially creating pockets where entropy doesn't just stall, it temporarily reverses. Picture a wave rolling backward or a gust of wind sucking smoke back into a chimney. These anomalies don't break the second law, they bend it, proving that entropy isn't a tyrant, it's more like a referee in a game where the rules have hidden loopholes. The implications are staggering. If quantum fluctuations can tweak entropy's grip, even momentarily, it raises the question. Could the universe's largest structures, voids, filaments, even dark matter halos, owe their existence to these tiny, rebellious acts of order? Some theories suggest that the seeds of galaxy formation might have been planted by quantum ripples in the early universe, amplified over billions of years into the cosmic web we see today. Others propose that dark energy itself could be entangled with these fluctuations, as if the vacuum's restless energy is tugging spacetime apart from within. But the real mind-bender is this: if entropy can dip locally, even for a split second, what does that mean for time? The arrow of time, the one-way flow from past to future, is intimately tied to entropy's rise. So if quantum effects can nudge disorder backward even fleetingly, does time itself stutter in those moments? It's a question that blurs the line between thermodynamics and metaphysics, suggesting that the universe's most fundamental laws might be far more flexible and far stranger than we ever imagined. One thing's certain, the quantum realm refuses to be ignored. From the void between stars to the birth of galaxies, its whispers are etched into the cosmos. And if entropy isn't as absolute as we thought, then maybe, just maybe, the universe still has surprises up its sleeve. The Big Bang should have been chaos incarnate, a seething, disordered fireball where energy and matter collided in a frenzy. Yet when we look back at the universe's earliest moments, we find something baffling, an almost eerie lack of entropy. Instead of the expected cosmic pandemonium, the infant universe was astonishingly smooth, like a perfectly stirred cup of coffee with no clumps or swirls. This is the entropy problem, and it's one of cosmology's greatest unsolved puzzles. If the second law of thermodynamics holds true, entropy should always increase. So how did the universe start with such a pristine, low-entropy state? Inflation theory, the leading explanation for the Big Bang's aftermath, offers a partial answer. The idea is that a fraction of a second after creation, space itself expanded faster than light, stretching quantum fluctuations into the seeds of galaxies. But here's the catch. Inflation doesn't actually solve the entropy problem, it just kicks it down the road. Picture blowing up a balloon with microscopic wrinkles. As it inflates, those wrinkles smooth out, creating the illusion of order. But the wrinkles are still there, just stretched too thin to see. Inflation smooths the universe's initial conditions, but it doesn't explain why those conditions were so orderly to begin with. Some physicists argue this points to a gaping hole in our understanding, like finding a perfectly stacked deck of cards in the middle of a hurricane and being told, "Don't worry, shuffling will fix it." The mystery deepens when we consider what came before the Big Bang. If entropy always increases, then the pre-Bang universe, whatever it was, must have had even lower entropy, a state of near-impossible order. One radical proposal suggests time itself might be cyclical, with each Big Bang resetting entropy like a cosmic Etch-A sketch. Others speculate that our universe is just one bubble in a vast multiverse, where statistically, some bubbles will inevitably start with freakishly low entropy by sheer chance. But these ideas feel like placeholders, mathematical Hail Marys tossed into the void. What if the answer lies beyond thermodynamics? Some theorists are exploring the idea that gravity, not entropy, was the true architect of the early universe's order. In this view, gravity's pull acts as a kind of cosmic librarian, organizing chaos into structure against entropy's tide. Or perhaps entropy isn't a fundamental force at all, just a side effect of deeper, undiscovered physics like shadows on a cave wall. Whatever the solution, one thing's clear. The universe's first moments weren't just a hot mess. They were a carefully balanced act, a whisper of order in the dark. And until we understand why our cosmic story is missing its opening chapter, time's arrow has always pointed in one direction, forward. From the moment the universe began, entropy has been the invisible hand guiding this relentless march, ensuring that eggs don't unscramble and memories don't unform. But what if, in the depths of space, time's arrow isn't so rigid? What if entropy's grip loosens, allowing time to stutter, twist, or even reverse? Imagine a star that doesn't age, a celestial Benjamin Button, growing younger as the cosmos around it grows older. This isn't just science fiction, it's a real possibility if entropy behaves differently in the void. Take the hypothetical case of an anti-aging star in a region of space where entropy temporarily decreases. Normally, stars burn fuel, exhaust their cores, and fade into stellar corpses. But if entropy reversed locally, the star might begin absorbing scattered radiation, its nuclear fires reigniting as it retraces its life cycle backward. Gas and dust would flow inward instead of exploding outward, and the star's light would grow brighter, not dimmer. From our perspective, this would look like time running in reverse, a cosmic VHS tape played backward. The implications are staggering. If time's flow depends on entropy and entropy can falter, then causality itself, the bedrock of physics, might be negotiable in deep space. This isn't just about stars. Black holes already warp time so severely that near their event horizons, clocks tick infinitely slow from an outsider's view. If entropy adds another layer of complexity, time near a black hole might not just slow, it could fracture. Picture a spaceship orbiting a black hole where entropy fluctuates wildly. One moment, the crew watches a planet age millions of years in seconds. The next, they see a nebula collapse into a star, as if the universe hit rewind. These aren't mere thought experiments. Quantum mechanics already allows for microscopic reversals of entropy, so why not macroscopic ones in the extreme environments of space? The real puzzle is causality, the idea that causes must precede effects. If entropy dips, could an event's consequence appear before its cause? Some theories suggest that in regions of negative entropy, information might travel backward in time, creating loops where the future influences the past. It's like throwing a rock into a pond and seeing the ripples converge before the splash. While this defies our everyday intuition, the universe has never been obligated to make sense to humans. The stakes are cosmic. If time's arrow isn't universal, then the history of the universe might not be a straight line. It could be a tangled web with threads running in all directions. Galaxies might form from future collisions, and black holes could birth the stars that birthed them. It's a dizzying thought, but one that forces us to ask, is time fundamental or just an emergent property of entropy's dance? The answer could redefine not just physics, but reality itself. What if our universe isn't special, just lucky? The multiverse theory throws open a dizzying possibility, an infinite tapestry of parallel realities, each with its own laws, its own physics, even its own flavor of entropy. In this cosmic lottery, most universes might be born in chaos, their energy scrambled into useless noise from the first instant. But ours hit the jackpot. Starting with inexplicably low entropy, it had just the right conditions for stars to ignite, planets to form, and life to emerge. This isn't just a wild guess. It's a potential solution to one of cosmology's biggest head-scratchers. Why did our universe begin with such unnatural order? Picture a foam of bubbles in a sink, each representing a separate universe. Most pop immediately, their energy too disordered to sustain structure. A few linger longer, their surfaces trembling but intact. Now imagine one bubble ours that somehow stays perfectly spherical, its entropy so finely tuned that galaxies can condense like dew on its surface. Statistically, this seems impossible. But in an infinite multiverse, even the rarest events become inevitable. We might not live in a special universe. We might just live in the only kind of universe where beings like us could ever ask the question. The implications ripple outward. If most universes are high-entropy wastelands, then the arrow of time, the one-way flow from past to future, might not be universal. Some realities could flicker into existence with time already broken, their causality scrambled like a shattered mosaic. Others might oscillate between order and chaos, their entropy rising and falling like a pendulum. And in the darkest corners of this cosmic landscape, universes could exist where entropy runs backward entirely, their histories unfolding from chaos to order like a film in reverse. But here's the twist. Even if the multiverse explains our low entropy beginnings, it doesn't answer everything. Why does gravity seem to fight entropy's rise, sculpting galaxies from the void? Could some universes have different forms of thermodynamics altogether, with entirely new laws governing disorder? And if we're just one bubble in an infinite froth, what does that say about the nature of reality? The multiverse doesn't simplify the mystery, it magnifies it, revealing layers of complexity we're only beginning to fathom. Perhaps the most humbling thought is this: if entropy defines the boundaries of possible universes, then life itself might be a fleeting anomaly. Most cosmic neighborhoods would be too chaotic for atoms to bond, let alone for thought to flicker into being. We're not just riding entropy's current, we're surfing its razor's edge, balanced between order and chaos in a universe that somehow, against all odds, got the numbers just right. And that makes every moment, every star, every planet, every conscious thought a statistical miracle in a sea of infinite possibilities. NASA's deep space observations keep revealing puzzles that defy textbook thermodynamics. Take galaxy clusters, those sprawling metropolises of stars bound by gravity. When astronomers measured their heat distribution using X-ray telescopes, they found something bizarre. The gas between galaxies wasn't cooling down as fast as entropy's rules would predict. It's like throwing a hot iron bar into a freezer, only to watch it stay glowing red for billions of years. Some regions even showed patches of gas that were warmer than their surroundings, as if invisible cosmic stoves were flickering on in the void. Then there's the mystery of cosmic rays, high-energy particles racing through space at nearly light speed. As these particles travel, they should lose energy steadily, like a rolling ball slowing on rough terrain. But detectors like the Alpha Magnetic Spectrometer on the International Space Station keep catching rays with more energy than expected, as if something out there is secretly recharging them. These aren't just measurement errors. They're cosmic glitches that hint at gaps in our understanding of how energy and disorder truly behave in deep space. Enter the James Space Telescope, peering further back in time than any instrument before it. Its infrared eyes have spotted ancient galaxies that glow too brightly, too soon after the Big Bang. According to conventional models, these galaxies shouldn't have had enough time to accumulate such staggering amounts of ordered starlight, not unless entropy worked differently in the early universe. Some researchers speculate that gravity's grip might have temporarily thermodynamics in those dense primordial conditions, creating pockets where heat flowed backward or energy concentrated unnaturally. The most tantalizing clue comes from black hole jets, colossal beams of plasma shooting from active galaxies at nearly light speed. These jets somehow channel chaotic energy into perfectly focused streams, defying entropy's tendency to scatter everything into randomness. It's as if the universe has hidden plumbing, funneling chaos into order on scales we can barely comprehend. What if these anomalies aren't exceptions but signposts? Each one could be pointing toward a grander thermodynamic, one where entropy flexes and adapts to the universe's most extreme environments. Maybe galaxy clusters have their own entropy gradients, shaped by dark matter's invisible scaffolding. Or perhaps cosmic rays are tapping into quantum fluctuations, borrowing order from the vacuum itself. The deeper we look, the clearer it becomes. Thermodynamics in deep space might not be broken. It might just be playing a game we're only beginning to understand. String theory rewrites the rulebook of reality by suggesting that the universe isn't just made of particles, it's woven from tiny, vibrating strings. These strings don't just dance in the 3 dimensions we know, they thrash through 10 or more, hidden from our perception like shadows on a wall. And here, where entropy gets a radical makeover. In this multi-dimensional landscape, chaos isn't just about disorder. It's about how these strings vibrate, twist, and tangle across unseen dimensions. Picture a symphony where every note is a string's vibration, and entropy becomes the measure of how wildly those notes clash or harmonize. This isn't just theoretical jazz. String theory's version of entropy might be the missing link between quantum mechanics and gravity, 2 realms of physics that have stubbornly refused to play nice. Quantum rules govern the tiny, where particles pop in and out of existence. Gravity shapes the cosmos, bending spacetime itself. Entropy in string theory could be the translator between these languages. Imagine black holes again. In relativity, they're simple gravitational pits. But string theory suggests their event horizons are frenzied tangles of strings, their entropy encoded in the way those vibrations interact with hidden dimensions. Suddenly, Hawking radiation isn't just a quantum fluke, it's the echo of strings rearranging themselves in higher dimensional space. The implications ripple further. If entropy ties into these extra dimensions, it could explain why the universe seems fine-tuned for life. Some string models suggest that the landscape of possible universes, each with different string vibrations, naturally filters out high-entropy realities. Ours, with its improbably low initial entropy, might be one of the rare configurations where strings vibrate in just the right harmony to allow galaxies, stars, and ultimately observers. It's as if entropy isn't just a force but a cosmic curator, selecting which universes get to tell a story. But there's a catch. String theory's thermodynamics isn't just about chaos, it's about information. Every string's vibration carries data, and entropy becomes a measure of how that information scrambles. In black holes, for instance, the strings at the event horizon might not just radiate energy. They could be projecting scrambled quantum code into the universe, like a corrupted hard drive spewing fragments of files. This idea, called the holographic principle, suggests that entropy isn't a property of objects, but of the information describing them. Your coffee cup cools not because of some abstract law, but because the strings encoding its heat are vibrating their secrets into the void. The real mind-bender: if string theory is right, entropy might not even be fundamental. It could emerge from deeper, more geometric rules, like how temperature emerges from the jiggling of atoms. Some theorists propose that entropy in higher dimensions is just a shadow of string entanglement, a phenomenon where strings in unseen dimensions intertwine in ways that project disorder into our 3D world. It's as if the universe has been running a thermodynamic simulation this whole time, and we're only now glimpsing the code. Of course, string theory remains unproven, and its thermodynamic twists are still speculative. But if even a fraction of this holds true, entropy stops being a mundane law of decay and becomes a cosmic language, one that might finally unite quantum weirdness with gravitational grandeur. And that's a revelation worth tuning into. What if you're not really you, just a momentary flicker of consciousness conjured from the chaos of the cosmos? Enter the brain, one of physics' most unsettling thought experiments. Named after the 19th century physicist Ludwig, this paradox suggests that in an infinite universe ruled by entropy, random fluctuations could spontaneously assemble a fully formed, self-aware mind, complete with fake memories, imagined surroundings, and even illusory knowledge of physics. No body, no history, no universe. Just a lone brain floating in the void, convinced it's real. Here, how it works. Entropy tells us disorder always increases, but tiny pockets of order can emerge by chance, like waves briefly cresting in a stormy sea. Given enough time, and the universe has near-infinite time, those fluctuations could theoretically arrange particles into anything, even something as complex as a working brain. Statistically, it's vanishingly unlikely. But in an eternal cosmos, unlikely doesn't mean impossible. In fact, over incomprehensible eons, brains should outnumber real, evolved minds by an unimaginable margin. So if you're betting on odds, the universe probably doesn't exist. You're just a fluke. This isn't just a philosophical brain teaser. It cuts to the heart of entropy's cosmic role. If disorder reigns supreme, why does our universe appear so structured? Why do we see galaxies, planets, and laws of physics instead of a formless haze? The brain suggests we shouldn't. A high-entropy universe would spend almost all its time in chaos, making fleeting moments of order, like our reality, statistical anomalies. The fact that we're here, observing a universe that's billions of years old and filled with structure, implies something's missing from the equation. Some physicists argue this paradox exposes a fatal flaw in how we think about entropy. Maybe the second law isn't absolute, Or perhaps the universe began with a cosmic reset that erased any prior chaos. Others propose that consciousness itself plays a role in shaping reality, that observation somehow freezes entropy's dice mid-roll. The wildest interpretation: our universe is a simulation, and brains are glitches in the code, momentary sparks of awareness in an otherwise indifferent void. But the most profound implication is this: if entropy can birth a self-aware mind from pure randomness, then reality might not have any deeper meaning at all. We could be accidental scribbles on the canvas of chaos, destined to dissolve back into the noise. Or perhaps the paradox is a signpost, pointing toward a hidden layer of physics where entropy and consciousness intertwine. Either way, the brain doesn't just question the nature of the universe, it questions whether we can trust our place in it. And that's a thought that lingers long after the equations fade. Wormholes have long been the stuff of science fiction, cosmic tunnels bending spacetime to connect distant points in the universe. But what if these hypothetical shortcuts don't just bridge space? What if they also bend the rules of entropy, creating corridors where disorder doesn't just spread, it leaps? Recent breakthroughs in theoretical physics suggest wormholes might not just be gravitational curiosities. They could rewrite thermodynamics itself. Picture a river flowing downstream, carrying leaves and debris, the usual march of entropy. Now imagine a hidden pipe beneath the riverbed, siphoning chaos from one bend to another without the usual meandering. That's the tantalizing possibility with wormholes. Entropy might not need to take the scenic route. The math gets wilder. Studies on traversable wormholes, those theoretically stable enough to pass through, reveal that their throats could act like thermodynamic express lanes. Normally, entropy increases as energy disperses, like ink diffusing in water. But inside a wormhole's twisted geometry, that diffusion might skip steps, tunneling disorder directly from one end of the universe to the other. It's as if the universe has secret where chaos doesn't just creep, it teleports. Some models even suggest that wormholes could temporarily lower entropy in localized regions, like cosmic refrigerators chilling pockets of spacetime. Here, where it gets truly mind-bending, if wormholes can shuttle entropy, they might also blur causality. Imagine a wormhole linking two points in time. Entropy leaking from the future into the past could create thermodynamic paradoxes, like a shattered glass reassembling itself before it's even dropped. Recent papers exploring quantum entanglement in wormholes hint that these structures might not just transport matter or energy. It could transmit information about disorder instantaneously, as if the universe's chaos ledger updates across light years in a blink. But there's a catch. For a wormhole to stay open, it needs exotic matter with negative energy, a substance that defies everything we know about physics. Yet here's the twist: quantum fluctuations in the vacuum of space already exhibit traces of negative energy, teasing the possibility that nature might have already paved the way for these entropy shortcuts. If so, wormholes wouldn't just be spacetime wrinkles. They'd be thermodynamic loopholes, threading chaos through the fabric of reality like a needle through cloth. The implications are cosmic. If entropy can tunnel, then black holes, long thought to be entropy traps, might be secretly linked to distant regions of the universe, their hidden disorder echoing across the void. Galaxies separated by billions of light years could share thermodynamic whispers, their fates entangled in ways we're only beginning to decipher. And if wormholes really can tweak entropy's rules, they might offer a not just through space, but through time itself, reshaping our understanding of the universe's beginning, end, and everything in between. One thing's certain: the deeper we dig into wormholes, the clearer it becomes that entropy isn't just a force, it's a player in a game far stranger than we ever imagined. And if these cosmic tunnels exist, they're not just rewriting the laws of physics. They're rewriting the very definition of chaos. Dark matter doesn't just lurk unseen. It might be the universe's silent choreographer, subtly guiding Entropy's dance on a cosmic scale. We can't see it, touch it, or even detect it directly, yet its gravitational fingerprints are everywhere, from the way galaxies spin faster than they should to the way light bends around invisible masses. But here's the twist. Dark matter's influence might extend far beyond gravity. Simulations of galaxy formation reveal something startling. Without dark matter's gravitational scaffolding, galaxies would tear themselves apart, their stars scattering into the void like leaves in a storm. Yet somehow these vast structures remain stable for billions of years, as if something, or someone, is quietly fine-tuning the balance between order and chaos. Dig deeper and the plot thickens. In supercomputer models that track the evolution of the cosmos, dark matter doesn't just hold galaxies together, it seems to regulate entropy itself. Picture a cosmic thermostat, constantly adjusting the flow of disorder to keep the universe from tipping into either perfect chaos or perfect order. In these simulations, dark matter's invisible particles interact in ways that smooth out entropy's extremes, creating pockets where stars can form and life can emerge. It's as if the universe has a hidden set of scales, with dark matter on one side and entropy on the other, and the slightest imbalance could unravel everything. But how? One theory suggests dark matter might be interacting with itself through unknown forces, creating a kind of entropy buffer. Imagine a sponge soaking up excess chaos, then slowly releasing it back into the cosmos over eons. Another idea points to dark matter's role in shaping the cosmic web, the vast, filamentary structure of the universe. These filaments, woven from dark matter's gravity, could act like highways for entropy, channeling disorder away from galaxies and into the voids between them. It's a cosmic redistribution system, ensuring no single region gets overwhelmed by chaos. The implications are staggering. If dark matter really is entropy's invisible hand, it could explain some of the universe's deepest mysteries. Why did the early universe have such unnaturally low entropy? Dark matter might have set the stage, sculpting the conditions for order to emerge. Why do galaxies resist the pull of entropy for so long? Dark matter could be their unseen anchor, steadying them against the tide. And if dark matter's entropy stabilizing effects are real, they might hint at entirely new physics, a shadow realm of particles and forces that don't just shape space, but time itself. The irony is delicious. The very substance we've struggled to detect for decades might be the key to understanding why the universe isn't a featureless sea of disorder. Dark matter doesn't just fill the gaps in our maps of the cosmos, it might be filling the gaps in our understanding of thermodynamics. And if that's true, then the search for dark matter isn't just about finding missing mass. It's about uncovering the hidden rules of reality. The cosmic microwave background is like the universe's baby picture, a faint glow left over from when the cosmos was just 380,000 years old. But this isn't just a snapshot. It's a fossilized record of entropy's earliest moments, imprinted in subtle temperature variations no stronger than a few millionths of a degree. These tiny fluctuations might seem insignificant, but they're the blueprints for everything that followed, the seeds of galaxies, the scaffolding of the cosmic web. And buried in their pattern could be clues that entropy didn't play by the rules we think we know. Take the so-called cold spot, a bizarre region in the CMB where temperatures dip lower than any model predicts. It spans nearly 2 billion light-years, a cosmic bruise that shouldn't exist if entropy had spread evenly after the Big Bang. One explanation: this might be the scar of a collision with another universe, a bubble from the multiverse where entropy operated differently, leaving a thermodynamic fingerprint on our own. Or consider the CMB's large-scale asymmetry. One half of the sky shows slightly stronger temperature variations than the other, as if the universe's chaos wasn't evenly distributed from the start. It's like cracking open an egg to find the yolk off-center, a hint that something fundamental about entropy's behavior is missing from our equations. Then there's the mystery of the CMB's missing correlations. On the largest scales, temperature fluctuations don't align the way standard thermodynamics predicts. Some scientists argue this could mean entropy wasn't just passively increasing in the early universe. It might have been actively sculpted by forces we haven't discovered yet. Imagine gravity and dark energy as two painters working on the same canvas, one brushing order into existence while the other smears chaos across the void. The CMB's anomalies could be their competing strokes frozen in time. The most tantalizing possibility, these imperfections might not be random. Advanced algorithms analyzing the CMB have detected strange, concentric patterns, circles within circles where temperatures fluctuate with unnatural regularity. Some theorists suggest these could be echoes of a pre-Big Bang universe, thermodynamic ripples from a cycle we don't yet understand. If true, it would mean entropy isn't linear at all, but cyclical, resetting with each cosmic rebirth. What's clear is this: the CMB isn't just a relic, it's a cipher waiting to be decoded. Every anomaly challenges the textbook version of thermodynamics, whispering that the universe's first moments were far stranger and far more ordered than we ever imagined. And if we can read its hidden language, we might finally understand why entropy chose the path it did and where it's taking us next. Consciousness might seem like an unlikely guest at entropy's cosmic table, but what if the two are secretly intertwined? At first glance, the idea sounds like science fiction, yet cutting-edge theories are probing a startling connection. The chaotic dance of particles in the universe could mirror the flickering patterns of thought inside our own minds. Take the human brain, a 3-pound universe of its own, where billions of neurons fire in a symphony of electrical storms. Neuroscientists measure this activity using something called neural entropy, a way to quantify the brain's chaos. When you're deep in thought or dreaming, your neural entropy spikes. During focused tasks, it drops. Now zoom out to the cosmic scale. The universe's entropy follows eerily similar rhythms, rising and falling in pockets where stars form or black holes collide. Could this be coincidence or something deeper? Some theorists argue that consciousness isn't just a product of low entropy conditions, it might actively sculpt them. Imagine the universe as a vast, self-organizing system where observation itself tames chaos. In quantum mechanics, the act of measurement collapses probabilities into definite states, as if reality crystallizes under our gaze. Extend this idea and conscious observers, whether humans, aliens, or future AI, might be thermodynamic anomalies, islands of order that briefly resist entropy tide. It's a modern twist on an old philosophical riddle. If a tree falls in a forest with no one to hear it, does it make a sound? The thermodynamic version asks, without a mind to witness it, does entropy fully exist? The wildest version of this idea comes from integrated information theory, which suggests consciousness arises from the complexity of a system's internal connections. Apply that to the cosmos, and the universe itself, with its tangled webs of galaxies and quantum fields, might harbor a faint, diffuse form of awareness. In this view, entropy isn't just a force, it's the universe's way of thinking, with black holes and supernovae as fleeting thoughts in a cosmic mind. Even the brain paradox fits here. If random fluctuations can spawn a self-aware entity, maybe the universe isn't just prone to consciousness, it's built for it. But here's the kicker. If consciousness and entropy are linked, it could mean the universe isn't just evolving toward chaos, it's evolving toward understanding. Every star that dies, every galaxy that forms, might be part of a grand computation, with entropy as the pencil scratching equations into space-time. The heat death of the universe, often seen as a bleak endgame, could instead be a final state of perfect equilibrium, not silence but sublime clarity. Of course, this is speculative territory. Critics dismiss it as poetic metaphysics, pointing out there's no measurable mechanism tying brain activity to galactic thermodynamics. Yet the parallels linger, haunting the edges of physics like a half-remembered dream. Whether coincidence or clue, one thing's certain. The deeper we dig into entropy's mysteries, the more the universe seems to whisper that chaos and consciousness might be two sides of the same cosmic coin. And that's a thought worth savoring. What if life elsewhere in the universe doesn't just tolerate entropy, it thrives on it? Picture a creature not of flesh and blood, but of swirling plasma and magnetic fields, drifting through the turbulent atmosphere of a gas giant. Instead of hunting for food, it feeds on the very chaos around it, absorbing entropy gradients like a plant soaking up sunlight. Or consider a civilization so advanced that they've tamed the second law itself, building megastructures that siphon disorder from dying stars to power their cities. These aren't just sci-fi fantasies. They're plausible scenarios if thermodynamics bends differently in the cosmos's hidden corners. Start with the basics. Life as we know it relies on energy gradients, differences in temperature, pressure, or chemistry that can be harnessed to do work. But what if some organisms evolved to exploit entropy gradients instead? In the crushing depths of an icy moon's subsurface ocean, where thermal vents are scarce, life might have learned to extract energy from the slow, inevitable unraveling of order into chaos. Imagine microbial colonies that function like living capacitors, storing pockets of low entropy to power their metabolisms during periods of cosmic calm. Or photosynthetic aliens that don't rely on photons, but on the statistical jitter of particles in a quantum vacuum, tapping into the universe's baseline disorder. Now scale up to intelligence. A species that perceives entropy not as an enemy, but as a resource, would engineer their world in ways we can barely fathom. Their machines might resemble Maxwell's demon, the mythical creature from physics' thought experiments that sorts fast and slow molecules to cheat the second law. Instead of burning fuel, their engines could harness the natural entropy flow between regions of space, like turbines placed in a cosmic river of disorder. Their cities might cluster around black holes or neutron stars, where extreme gravity creates steep entropy gradients perfect for energy extraction. And their greatest artworks, perhaps sculptures carved from spacetime itself, where they've temporarily reversed entropy's flow to create fleeting pockets of impossible order. But the real mind-bender is this: if life can manipulate entropy, could it also manipulate time? A civilization that masters disorder might treat causality as a suggestion, not a rule. Their historians could read the entropy imprints left in ancient light, reconstructing events we'd consider lost to time. Their explorers might ride entropy waves across galaxies, surfing the universe's chaotic tides like sailors catching the wind. And their philosophers, they'd likely see the heat death of the universe not as an end, but as a canvas, a state of maximum disorder from which new forms of order could emerge, like phoenixes rising from thermodynamic ash. Irony is delicious. We spend so much energy fighting entropy, cleaning our rooms, repairing our machines, prolonging our lives, that we forget it's the engine of change itself. An alien species built around entropy wouldn't just survive the universe's chaos. They'd dance with it, turning the cosmos's slow unraveling into a symphony. And that's the most humbling thought of all. Our way of life might not be the rule, but the exception. A fleeting spark of order in a universe that prefers its rhythms wild. Simulation theory takes the mystery of entropy and flips it on its head. What if the universe's thermodynamics aren't laws of nature, but lines of code? Imagine the cosmos as an advanced simulation, where entropy isn't just a force but a programmed variable, tweaked to keep the universe running smoothly, or to reveal its artificial seams. Think of a video game where fire spreads realistically or water flows downhill. These aren't miracles of nature, they're scripted behaviors designed to mimic reality. Now scale that up to the universe. The way heat disperses, stars burn out, even the arrow of time itself. Could these just be algorithmic rules written into the fabric of our simulated existence? The glitches in this cosmic program might already be visible. Take the low entropy state of the early universe, a condition so statistically unlikely that some physicists compare it to shuffling a deck of cards and getting them all in perfect order. In a natural universe, this makes no sense. But in a simulation, it's like a developer initializing a clean, optimized environment before launching the program. And those anomalies in the cosmic microwave background, the cold spots, the asymmetries, could be artifacts of the code, patches applied to keep the simulation stable as it scales up. Even black holes, those cosmic data sinks where information seems to vanish, might not be thermodynamic oddities at all. They could be the universe's garbage collectors, compressing and deleting unnecessary data to free up processing power. Here, where it gets eerie. If entropy is programmed, its quirks might not be random. The brain paradox, where self-aware minds spontaneously emerge from chaos, could be a way for the simulation to test its own consistency. Or consider dark energy, the mysterious force accelerating the universe's expansion. What if it's not a physical phenomenon but a buffer, a way to prevent the simulation from overloading as entropy piles up? Even quantum fluctuations, those tiny flickers of particles in and out of existence, might just be background processes, the universe's way of rendering reality on the fly. But the real kicker is this: if we're living in a simulation, entropy's rules aren't fixed. They're adjustable. A civilization running the program could tweak them at will, experimenting with different versions of physics like a player adjusting difficulty settings. Maybe our universe is just one iteration in an endless series of tests, each with slightly different thermodynamic parameters. And if that's true, the ultimate fate of the cosmos, whether it ends in heat death, a big crunch, or something stranger, might not be written in stone. It could be waiting for an update. Of course, this is all speculation. There's no hard evidence that we're living in a simulation, let alone that entropy is part of its code. But the idea forces us to ask a deeper question. If the universe's chaos isn't fundamental, what else might be up for negotiation? Time, gravity, reality itself. Simulation theory doesn't just challenge our understanding of entropy. It turns the cosmos into a cosmic mystery box, one where the rules we take for granted might just be placeholders for something far weirder. And that's a thought worth chewing on. Quantum mechanics and gravity have always been the unruly siblings of physics, one ruling the tiny world of particles, the other shaping the cosmos, yet refusing to play by the same rules. But what if entropy is the secret handshake that finally brings them together? Enter loop quantum gravity, a daring theory that suggests spacetime isn't smooth and continuous, but stitched together from tiny, indivisible atoms of reality. These fragments, far smaller than an atom's nucleus, vibrate and interact in ways that could rewrite how we understand chaos itself. Picture spacetime as a tapestry woven from threads so fine they're invisible to our best instruments. In loop quantum gravity, these threads form loops, tiny, interconnected rings that twist and knot into the fabric of the universe. The kicker: these loops don't just define space and time, they also carry entropy in ways that defy classical physics. Unlike the smooth, predictable rise of disorder we're used to, entropy in this granular universe might jump in discrete steps, like a dial clicking between settings rather than sliding continuously. Imagine heating a pot of water and seeing the temperature leap from lukewarm to boiling without passing through the degrees in between. That's the kind of quantum weirdness we're dealing with here. Now zoom in on a black hole's event horizon. In relativity, it's a smooth boundary, but loop quantum gravity paints it as a frenetic swarm of these spacetime atoms, each contributing a tiny bit of entropy to the whole. The math reveals something astonishing. The total entropy of a black hole isn't just proportional to its surface area. As Stephen Hawking proposed, it's quantized, coming in precise, countable units. It's as if the universe keeps its books not with rough estimates, but with exact, integer entries. This could explain why black holes don't just evaporate into randomness. Their entropy might be locked into these discrete packets, releasing chaos in controlled bursts like a cosmic metronome. But the real magic happens when these quantum gravity effects scale up. In the early universe, when all of existence was crammed into a space smaller than a grape, the discrete nature of spacetime could have forced entropy into unnatural patterns. Think of shaking a box of marbles. They'll settle into low entropy arrangements more often than you'd expect, simply because there are only so many ways they can fit together. This might solve the mystery of why the Big Bang started with such inexplicable order. The universe didn't have room to be chaotic. Its entropy was bottlenecked by the finite number of spacetime atoms available, like a deck of cards too small to shuffle properly. The implications ripple far beyond black holes and cosmic origins. If spacetime is granular, then entropy itself might have a resolution limit, a smallest possible unit of disorder. This would mean the second law isn't just a statistical trend, but a consequence of deeper geometric rules. Gravity, often seen as entropy's opponent because it creates structure, could actually be its choreographer, guiding how these spacetime atoms interact to produce the large-scale chaos we observe. Even dark energy's acceleration of the universe might trace back to these quantum grains, their collective behavior stretching the cosmos like a woven blanket unraveling at the seams. Loop quantum gravity is still speculative, and its thermodynamic twists are far from proven. But if it's right, entropy isn't just a side effect of the universe's laws, it's a direct window into the quantum architecture of reality. The chaos we see around us, from cooling coffee cups to dying stars, might be the echoes of spacetime's tiniest vibrations. And that's a clue worth chasing, because if we can decode entropy's quantum origins, we might finally solve physics' greatest puzzle: how to stitch gravity and the quantum world into a single, seamless whole. Neutron stars are cosmic pressure cookers, crushing matter into states so extreme that the usual rules of physics start to fray. Imagine taking the mass of our sun and squeezing it into a sphere the size of Manhattan. That's the mind-bending density we're dealing with. Here, protons and electrons merge into neutrons, creating a superfluid sea so perfect it defies viscosity, flowing without friction like some exotic quantum syrup. But beneath this eerie smoothness lies a thermodynamic puzzle. How does entropy, the universe's relentless push toward disorder, behave in an environment where quantum weirdness and gravitational might collide? The answer might rewrite our understanding of chaos itself. On Earth, entropy thrives in messy systems. Think of a shattered glass or a dissipating cloud of steam. But neutron stars are different. Their interiors are so densely packed that quantum effects dominate, forcing particles into highly ordered states despite the crushing pressure. It's like stuffing 1 billion pianos into a closet and hearing them play in perfect unison. This paradoxical ordering chaos suggests entropy here isn't just about disorder. It's about how quantum information scrambles in unimaginably tight spaces. Recent simulations reveal something even stranger. Neutron star matter might achieve minimum entropy states, where quantum correlations between particles reduce chaos to a whisper. Picture a deck of cards that somehow shuffles itself into perfect order, not by magic, but by the sheer force of quantum entanglement. Then there's the star's surface, a blistering crust of crystalline neutrons layered over that core. Here, entropy takes on a split personality. The crust behaves like a rigid solid, its entropy increasing as it absorbs energy from stellar quakes and magnetic flares. But dive a kilometer deeper, and entropy seemingly plateaus, as if the core's quantum rules hit a thermodynamic ceiling. This sharp divide hints at a hidden relationship between entropy and spacetime's granularity, like discovering that chaos has a resolution limit, beyond which it simply can't scale. The real revelation comes when neutron stars collide. These apocalyptic mergers spray out gravitational waves and gamma-ray bursts, but they also eject strange, ultra-dense matter that defies classification. Observations suggest the debris might form a fleeting quark-gluon plasma, a state of matter so primordial it hasn't existed since the Big Bang's first microseconds. In this plasma, entropy doesn't just rise, it oscillates, as if the universe is momentarily rewinding its own chaos. It's the thermodynamic equivalent of watching a shattered vase reassemble midair, then explode again in slow motion. What does this mean for entropy's quantum origins? If neutron stars can locally defy the second law's inevitability, even briefly, it suggests disorder isn't just a statistical trend. It's an emergent property of deeper quantum mechanical rules. Some theorists argue these stars are cosmic laboratories, their extreme conditions revealing how entropy emerges from the tiniest threads of spacetime. Others propose that neutron stars might harbor information vortices, where quantum data circulates without dissipating, like a whirlpool that never loses energy. One thing's certain, in the heart of a neutron star, entropy isn't the villain we know on Earth. It's a subtler, more nuanced force, one that might hold the key to unifying quantum mechanics and gravity. And if we can decode its behavior here in the universe's most extreme environments, we might finally understand how chaos truly shapes the cosmos. Black holes have long been the ultimate vaults of the cosmos, swallowing stars, light, and seemingly information itself. But what if nothing truly vanishes? The information paradox, first highlighted by Stephen Hawking, suggests that black holes might erase the quantum information of whatever falls in, violating a fundamental rule of physics: information must be conserved. Yet through entropy's lens, this paradox takes on a startling new shape. Imagine a library where books aren't burned but pulped into unrecognizable pulp. Their words still exist, just scrambled beyond immediate recognition. That's the emerging view of black holes. They might not destroy information, but remix it into a form we don't yet understand, with entropy acting as the cipher. Consider the event horizon's surface, a buzzing membrane of quantum fluctuations where particles and antiparticles constantly pop into existence. As matter crosses this boundary, its information doesn't simply disappear. It's imprinted onto the horizon's fabric like a hologram, encoded in microscopic bits of entropy. Each bit represents a tiny piece of the fallen object's quantum state, preserving its essence in a scrambled, thermalized form. It's as if the black hole is performing a cosmic shred-and-reconstruct operation, turning a star's orderly atomic structure into a chaotic but traceable pattern of entropy. The math behind this, called the AD-SCFT correspondence, suggests that the 3D universe we see might be a projection of information stored on a 2D surface, with black holes as the ultimate data compressors. But here's the twist. If entropy encodes information, could it also preserve the universe's memory? Think of a photon that's spent billions of years traveling across space. Its journey, every interaction, every deflection is etched into its quantum state. When it finally plunges into a black hole, that history isn't erased. It's translated into entropy's language, woven into the hole's ever-growing disorder. Over time, as the black hole emits Hawking radiation, that information might slowly leak back out, like a message in a bottle bobbing to the surface of spacetime. This wouldn't be a neat reconstruction, more like reassembling a shattered vase from dust, but the blueprint would remain. The implications ripple far beyond black holes. If entropy is the universe's archival system, then every event, from a supernova's explosion to a thought flickering in your brain, might leave an imprint on spacetime's fundamental structure. Dark matter's gravitational whispers, the afterglow of the Big Bang, even the trajectory of extinct civilizations, all could be stored in the cosmic ledger of entropy, waiting to be decoded. Some theorists speculate that this might resolve the Fermi paradox. Advanced civilizations could have left thermodynamic messages in the fabric of space, artifacts not of metal or light, but of carefully engineered entropy gradients. Yet the biggest question remains. If entropy is memory, what does it remember for? Is the universe merely keeping receipts, or is there a deeper computation at work, a cosmic program running on the substrate of chaos? The answer might lie in the holographic principle's most radical interpretation. That reality itself is a dynamic interplay between order and disorder, with black holes as the hinges between the two. Every time a star collapses or a particle decays, entropy doesn't just increase, it evolves, carrying forward the universe's story in a language we're only beginning to decipher. And that story, it turns out, might be far from over. Cosmic strings are like the universe's stretch marks, hypothetical scars left over from the violent birth of spacetime, thinner than an atom but stretching across billions of light years. These bizarre defects aren't just relics. They could be cosmic highways for entropy, channeling disorder through the universe like wires conducting electricity. Picture a spiderweb threaded through the void, each strand vibrating with enough energy to warp spacetime itself. If they exist, these strings wouldn't just sit idly. They'd actively redistribute chaos, bending the rules of thermodynamics in ways we're only beginning to imagine. Take a single cosmic string, thinner than a proton but with the mass of a mountain range packed into every inch. Its gravitational pull is so intense that it could slice through galaxies like a hot knife through butter, leaving ripples in spacetime in its wake. But here, where entropy enters the picture. As these strings vibrate and twist, they might act as cosmic lightning rods for disorder, absorbing entropy from their surroundings and flinging it light years away. Imagine a whirlpool in the ocean, sucking in turbulent water and spitting it out elsewhere. Except in this case, the whirlpool is a crack in reality, and the water is the universe's chaos. The math gets even wilder. Some models suggest cosmic strings could create entropy shadows, regions where disorder temporarily dips because the strings have siphoned it away. It's like walking into the shade on a scorching day, only instead of escaping sunlight, you're stepping into a pocket of unnatural order. These shadows might explain why certain regions of space, like the cold spots in the cosmic microwave background, defy thermodynamic expectations. If cosmic strings are lurking out there, they could be stealthily rearranging the universe's chaos behind the scenes. But the real kicker, cosmic strings might not just move entropy, they could generate it. Quantum effects near these ultradense filaments could spawn particles out of pure vacuum, a process that dumps fresh disorder into the cosmos like a factory churning out chaos. In this scenario, entropy isn't just spreading, it's being manufactured on an industrial scale, with cosmic strings as the assembly lines. And if these strings occasionally snap or loop into self-colliding knots, the energy released could trigger entropy surges, sudden waves of disorder rippling across spacetime like tsunamis. The implications are staggering. If cosmic strings are entropy's hidden architects, they could be the missing piece in puzzles ranging from galaxy formation to dark energy's grip on the universe. Maybe the reason the cosmos isn't a uniform soup of chaos is because these strings are quietly shepherding disorder, stitching it into the fabric of reality like invisible seamstresses. Or perhaps they're even older than entropy itself, relics from a time before the second law, when the universe ran on different rules altogether. One thing's certain, if cosmic strings are real, they're not just curiosities. They're active players in the universe's grand thermodynamic drama, twisting the plot in ways we've only begun to guess. And that means the story of entropy and reality itself might be far stranger than we ever dreamed. If the universe's expansion slams into reverse, collapsing all matter and energy back into a singularity, a big crunch, entropy might not just bend its own rules, it could shatter them entirely. Picture time running backward, shattered glass fragments leaping from the floor to reassemble in your hand. stars reigniting from scattered stardust and black holes disgorging their swallowed light. This isn't just poetic reversal, it's a thermodynamic possibility if gravity ever overpowers dark energy's relentless push. In a big crunch scenario, entropy wouldn't just decrease, it would invert, rewriting the second law's ironclad script. The universe's arrow of time, always pointing toward disorder, might flip direction, turning the heat-death narrative on its head. Contrast this with the heat-death hypothesis, where entropy reigns supreme. Here, the cosmos expands forever, stars burn out, black holes evaporate, and spacetime itself becomes a thin, cold soup of evenly dispersed particles. No gradients, no energy flows, just perfect, unchanging equilibrium. It's the ultimate victory for disorder, where even atomic motion grinds to a halt. But the Big Crunch offers a radically different finale, a universe that recycles itself, with entropy not as a silent executioner, but as a phoenix waiting to rise from the ashes. The physics behind this reversal hinges on gravity's hidden role in entropy's ledger. While we think of gravity as bringing order, shaping galaxies, forging stars, it's also a chaos multiplier. Black holes, the densest gravitationally bound objects, maximize entropy within their event horizons. But in a collapsing universe, gravity could become entropy's puppeteer. As matter and energy compress, quantum effects might dominate, reorganizing disorder into structured patterns. Imagine a deck of cards shuffled into randomness, then subjected to a machine that sorts them perfectly by exploiting microscopic vibrations. The Big Crunch could be that machine, leveraging gravitational collapse to reset entropy's clock. Yet there's a catch. For entropy to truly reverse, the universe would need to retrace its steps with perfect precision, a near-impossible feat. Quantum fluctuations, those tiny randomness generators, would ensure no two collapses are identical. Some theories suggest entropy might instead stutter, decreasing locally while increasing globally, like eddies in a reversing river. Others propose that a crunch wouldn't erase entropy but compress it, folding the universe's chaos into a seed for the next cosmic cycle. The stakes couldn't be higher. If entropy reverses, it implies time itself could loop, with each Big Bang Crunch cycle rewriting thermodynamics rules. But if heat death wins, entropy becomes the universe's final epitaph, a silent, infinite grave. Between these two fates, entropy isn't just a passive observer, it's the universe's ultimate architect, shaping not just how things fall apart, but whether they'll ever come together again. The answer might lie in the dark energy tug-of-war, or in quantum layers of reality we've yet to uncover. Either way, entropy holds the pen that writes the cosmos' final chapter. Testing how thermodynamics behaves in the depths of space isn't like running an experiment in a lab here on Earth. Out there, the rules bend in ways we can't easily recreate. Gravity warps spacetime, quantum effects dominate, and energies reach levels that would vaporize our best instruments. Even our most advanced probes can't venture close enough to black holes or neutron stars to take direct measurements, leaving us to piece together cosmic thermodynamics from faint whispers of light and ripples in spacetime. But that hasn't stopped scientists from getting creative. Take condensates, for example. These ultra-cold clouds of atoms, chilled to just a hair above absolute zero, behave like a single quantum entity, mimicking the bizarre, low-entropy conditions of the early universe. In labs, researchers have used these condensates to simulate how entropy might behave in extreme gravitational fields, watching as quantum effects temporarily defy the usual march toward disorder. It's like reconstructing a supernova with a box of firecrackers, not perfect, but it reveals patterns we'd never spot otherwise. Then there are quantum simulators, engineered systems that replicate the mind-bending physics of deep space using controlled environments. Some use arrays of lasers to mimic the warped spacetime near a black hole's event horizon, observing how entropy scrambles information in ways that defy classical thermodynamics. Others employ superconducting circuits to recreate the quantum fluctuations of cosmic voids, where particles flicker in and out of existence. These experiments can't perfectly replicate the vast scales of space, but they offer something just as valuable: a glimpse into how entropy might operate when gravity, quantum mechanics, and sheer scale collide. Even with these tools, the gaps are enormous. The universe operates on timescales and energies that dwarf anything we can reproduce. Black holes take eons to evaporate, dark energy's effects unfold over billions of years, and the quantum foam of spacetime fluctuates at scales trillions of times smaller than an atom. To bridge the divide, physicists are turning to indirect methods, like analyzing the afterglow of colliding neutron stars or hunting for anomalies in the cosmic microwave background. Each anomaly is a breadcrumb, hinting at entropy's hidden rules. The biggest challenge, entropy itself. In the lab, we're stuck studying closed systems, but the universe is anything but. Gravity pulls matter together, dark energy pushes it apart, and quantum fields hum with energy we can't yet measure. Untangling this cosmic web requires more than just better tools. It demands a revolution in how we think about chaos, order, and the fundamental nature of reality. Until then, every experiment, every simulation is a step toward answering the ultimate question. Is entropy the universe's rulebook, or just its first draft? If the laws of thermodynamics aren't as fixed as we've believed, the implications ripple far beyond physics. They unravel the very fabric of how we understand existence. Free will, for instance, has long been tangled with entropy's arrow. Think of every decision you've ever made: neurons firing, chemicals reacting, energy dispersing, all seemingly governed by the second law's push toward disorder. But what if entropy's rules flex in deep space? Suddenly, the deterministic chains that bind our choices might loosen. A universe where entropy fluctuates could introduce pockets of unpredictability, where cause and effect don't just bend, they shatter. Imagine a cosmic-scale game of dice, not just at the quantum level but woven into the macro world, where chaos isn't a flaw in the system but a feature. This isn't just hypothetical. Ludwig himself grappled with entropy's philosophical weight, arguing that our perception of time's flow, and by extension, free will, might be an illusion cast by statistical mechanics. His molecular chaos hypothesis suggested that while particles move randomly, their collective behavior creates the illusion of order. Fast forward to today, and modern physicists extend this idea. If entropy's rise isn't absolute, then time's arrow might not be either. In regions where entropy stutters or reverses, could consciousness, and with it, agency, operate differently? An alien civilization in such a zone might experience time as cyclical, their choices looping back like a strip of cause and effect. Then there's determinism, the idea that every event is the inevitable result of prior states. Classical thermodynamics seems to bolster this view. Energy disperses, systems equilibrate, and the future feels. But rewrite those laws and determinism's foundation cracks. If black holes leak information or quantum fluctuations locally reverse entropy, the universe stops being a clockwork machine. It becomes more like a kaleidoscope, where every turn introduces new, unpredictable patterns. Philosophers like David once argued that causation is just a habit of human perception. Modern entropy anomalies might prove him right. What we call laws could be mere statistical tendencies with room for cosmic exceptions. The nature of reality itself hangs in the balance. If entropy is a holographic projection, as some string theorists suggest, then disorder might not be fundamental, just a shadow of deeper geometric rules. This echoes Plato's allegory of the cave, where what we perceive as reality is just a flickering silhouette of truer forms. Even consciousness, often seen as an emergent property of low-entropy systems, might be part of the illusion. Or, as integrated information theory proposes, perhaps the universe is conscious because entropy binds information into meaningful structures, like a cosmic mind thinking itself into existence. History's greatest thinkers, from statistical revolutions to musings on life-negating entropy, have danced around these questions. Today's physicists pick up the thread, weaving entropy into theories of everything from multiverses to simulation hypotheses. The stakes: if thermodynamics is rewritten, we're not just updating textbooks. We're redefining what it means to exist, choose, and perceive. The universe might be less a machine and more a story, one where entropy isn't the author but the ink. And that changes everything. The next generation of space missions is gearing up to crack open entropy's cosmic secrets in ways we've never seen before. Take LISA, the Laser Interferometer Space Antenna, scheduled to launch in the 2030s. This revolutionary observatory won't just detect gravitational waves, it'll listen to the universe's thermodynamic heartbeat. Imagine tracking colliding black holes not just by their space-time ripples, but by the entropy fingerprints they leave behind. When two supermassive black holes spiral toward collision, their event horizons stretch and warp, scrambling information in ways that should leave distinct thermodynamic signatures in the gravitational waves they emit. LISA's ultra-precise lasers could catch these subtle distortions, revealing whether black holes truly are perfect entropy machines, or if something stranger happens when chaos meets gravity's ultimate grip. Then there's Athena, the advanced telescope for high-energy astrophysics, poised to launch in the 2030s. Unlike optical telescopes that show us where cosmic structures are, Athena's X-ray vision will show us how they're thermodynamically evolving. Galaxy clusters, those sprawling metropolises of hot gas and dark matter, should be entropy factories according to textbook physics. Yet existing telescopes keep finding bizarre temperature inversions where gas stays mysteriously hot for billions of years. Athena's unprecedented resolution will map these thermodynamic anomalies in 3D, hunting for patterns that could expose dark matter's hidden role in entropy's cosmic dance. One target: the so-called cold fronts regions where galaxy cluster gases show sharp temperature drops without the expected entropy changes. These might be evidence of cosmic strings or other exotic phenomena redistributing chaos across the universe. Meanwhile, NASA's mission, launching in the mid-2020s, will take an entirely different approach. Instead of focusing on massive objects, it'll scan the entire sky in infrared, hunting for the faint thermodynamic afterglow of primordial quantum fluctuations. These microscopic ripples from the Big Bang's first moments were the seeds of all cosmic structure, and their entropy signatures could reveal whether the early universe's improbable order came from quantum gravity effects we haven't discovered yet. All-sky maps might even spot thermodynamic anomalies in the cosmic microwave background that point to collisions with other universes, regions where entropy flowed backward in a neighboring bubble of reality. But perhaps the most daring experiment isn't a telescope at all. It's the planned quantum experiments in space mission. By creating ultra-cold quantum condensates in Earth's orbit, free from gravitational interference, scientists could simulate how entropy behaves near black holes or in the early universe's extreme conditions. Picture a cloud of atoms chilled to near absolute zero, where quantum entanglement creates order that defies classical thermodynamics. In space, these condensates could maintain coherence long enough to test wild ideas, like whether entangled particles can temporarily reverse entropy's local flow, or if spacetime's quantum foam has its own thermodynamic rules. What ties these missions together is a radical shift in perspective. We're no longer just observing the universe's chaos, we're learning to measure its thermodynamic language. From gravitational waves that carry entropy's echo to X-rays that reveal dark matter's organizing hand, these tools will transform entropy from an abstract concept into something we can map, quantify, and perhaps even manipulate. And if they uncover deviations from the second law in extreme cosmic environments, That wouldn't just rewrite physics, it would redefine our place in a universe where chaos might not be the final word after all. The universe has a way of surprising us. Just when we think we've mapped the edges of reality, it throws open a door to something stranger. Picture this, a distant future where entropy doesn't just rise, it crescendos into a singularity, a point where disorder peaks so violently that the very laws of physics unravel. This isn't science fiction. It's a legitimate possibility lurking in the equations of thermodynamics. We call it the entropy singularity, and it could be the universe's ultimate plot twist. Think of entropy like a cosmic hourglass. Right now, we're watching the sand trickle down, grains of order slipping into chaos. But what happens when the last grain falls? Conventional wisdom says the universe reaches heat death, a frozen, featureless equilibrium where nothing moves, nothing changes. Yet some theorists argue that maximum entropy might not be an end, but a transformation. When disorder hits its absolute limit, the fabric of space-time could fracture, birthing new physics we can't yet imagine. It's like shattering a glass so completely that the pieces reconfigure into something entirely new. The math behind this is both elegant and terrifying. In general relativity, singularities, like those inside black holes, are points where gravity becomes infinite and equations break down. An entropy singularity would be different, not a collapse of space, but a collapse of chaos itself. At this threshold, quantum fluctuations, normally tiny and fleeting, could dominate on macroscopic scales. Imagine a vacuum boiling with particles appearing and disappearing, not just at the atomic level, but across entire galaxies. These fluctuations might stitch together new spacetime, like a cosmic reset button pressed by pure disorder. But here's the twist. If an entropy singularity reboots the universe, could it remember its past? Some models suggest that the universe's memory might survive the transition, encoded in the very fabric of the singularity. It's like burning a book and having the ashes rearrange themselves into a new story, one that echoes the old. This idea, called conformal cyclic cosmology, proposes that our universe is just one iteration in an infinite cycle, each beginning with a low entropy state emerging from the ashes of the last. Then there's the wild card, dark energy. If the universe's accelerating expansion continues, entropy might not have the chance to reach a true singularity. Instead, dark energy could stretch spacetime so thin that particles lose the ability to interact entirely, creating a big rip where entropy becomes meaningless. No more heat, no more cold, just an unchanging void where physics itself fades into silence. Yet even here, there's room for speculation. Could quantum tunneling in this desolate landscape spawn a new universe, like a seed cracking open in frozen ground? The most radical idea, the entropy singularity isn't a death knell but a birth canal. Just as black holes might hide new universes in their cores, a universe saturated with chaos could give rise to something entirely unexpected. Think of ice crystallizing on a window. Out of randomness, structure emerges. If entropy maxes out, the universe might not just reset, it could upgrade, rewriting its own rules in the process. We're left with more questions than answers. Is the entropy singularity a true cosmic reboot or just a poetic metaphor for the unknowable? Will the universe end with a whimper, a bang, or something stranger still? One thing's certain. If disorder holds the key to creation, then chaos isn't the enemy, it's the architect. And that changes everything. Imagine a civilization so advanced they don't just obey the laws of thermodynamics, they rewrite them. Picture sleek orbital stations humming with quantum processors, their energy fields carving out pockets of perfect order amidst the universe's chaos. This isn't just futuristic fantasy. Theoretical blueprints for entropy manipulation already exist in physics labs. The most famous is Maxwell's Demon, that 19th century thought experiment about a microscopic gatekeeper sorting fast and slow molecules to create perpetual motion. But what happens when thought experiments become engineering schematics? When we're no longer passive observers of entropy's march, but active editors of cosmic disorder? The ethical dilemmas emerge instantly. If we could lower entropy in a region, say, by using nanoscale traps to filter thermal noise into usable energy, would that give us the right to? On Earth, such technology could solve energy crises, reverse aging, even halt ecosystems collapse. But zoom out to cosmic scales, and entropy manipulation looks less like innovation and more like ecological vandalism. The universe's heat death hinges on entropy's inevitable rise. By locally reversing it, we'd essentially be stealing order from the future, accelerating the demise of everything beyond our carefully curated bubbles. It's the ultimate tragedy of the commons scenario. What benefits a civilization now might doom countless others later. Then there's the question of who controls the chaos. History shows that power over energy sources defines empires, from steam engines to nuclear reactors. Entropy manipulation would dwarf these, offering control over time's arrow itself. Picture rival factions weaponizing entropic warfare, freezing enemy cities in perfect stasis while their own metropolises hum with negentropic abundance. Or worse, a malfunctioning entropy dam rupturing, unleashing pent-up disorder like a thermodynamic tsunami. Even benevolent applications raise concerns. If we could extend human indefinitely by maintaining low entropy states in our cells, would death become optional? And at what cost to a universe already fighting entropy's scarcity? Science fiction has long grappled with these quandaries. In Isaac's The Last Question, humanity spends eons trying to reverse universal entropy, only to discover the solution requires becoming godlike. Revelation Space series features the Inhibitors, ancient machines that exterminate civilizations dabbling in entropy reversal to preserve cosmic balance. These stories hint at a deeper truth. Taming chaos might not just be dangerous, it could be sacrilege. Indigenous cosmologies often view nature's cycles as sacred. Western science treats them as problems to solve. If we erase entropy's role as the universe's great leveler, do we risk unraveling something fundamental about existence itself? Yet the most fascinating possibility isn't misuse, it's unintended consequences. Black holes teach us that entropy and information are deeply linked. Mess with one and you alter the other. An entropy-engineered region might inadvertently scramble quantum data, erasing histories or spawning brains, those self-aware flukes born from chaos. Or consider dark energy. If it's truly entropy's shadow, tweaking disorder could destabilize spacetime's expansion, collapsing galaxies prematurely. The universe's laws have evolved over billions of years into a delicate balance. Our tinkering could trigger chain reactions we lack the perspective to foresee. Perhaps the answer lies in perspective. The same physics that makes entropy manipulation conceivable also suggests it's a zero-sum game. You can't destroy chaos, only move it, like shoveling snow from your driveway onto a neighbor's lawn. True wisdom might mean working with entropy rather than against it, like life already does. After all, every cell in your body thrives by temporarily exporting disorder to its surroundings. Scaling this principle, a mature civilization might seek harmony with the universe's thermodynamic flows, not dominion over them. They'd understand that some boundaries exist for reasons deeper than our current grasp, and that sometimes the greatest act of wisdom is leaving the hourglass unturned. From the searing hearts of black holes to the frigid expanse between galaxies, entropy isn't just a law, it's a shapeshifter, bending the rules of reality in ways that humble our earthbound physics. What we've learned is this: thermodynamics isn't some universal decree carved in stone. It's more like a dialect, changing its inflection when spoken by the cosmos's most extreme environments. Those textbook diagrams of heat flowing from hot to cold, they crumble near neutron stars where quantum effects create pockets of eerie order. The ironclad second law, it stutters in the presence of dark matter's invisible scaffolding, which seems to choreograph chaos on galactic scales. Even time's arrow, that sacred one-way flow from past to future, might wobble in regions where entropy temporarily backtracks, like a river briefly flowing uphill. This isn't failure, it's revelation. Deep space isn't some passive backdrop. It's an active laboratory where matter, energy, and information collide under conditions we can't recreate on Earth. The voids between stars aren't empty, they're humming with quantum fluctuations that tweak entropy's grip. Black holes aren't just entropy factories, they might be cosmic archivists encoding information in their event horizons. And dark energy. It could be entropy's shadow, stretching the universe thin while whispering clues about thermodynamics we've yet to decipher. Here's the thrilling part. Every anomaly, every paradox is a breadcrumb leading beyond our current understanding. The cold spot in the cosmic microwave background, the unnatural smoothness of the early universe, even the way galaxy clusters refuse to cool, they're not problems to solve. They're invitations to explore. Physics isn't ending, it's evolving with entropy as our guide through the wilderness. So keep staring at the night sky with wonder. That flicker of starlight, it's not just photons, it's a message from the frontier where the rules are still being written. The next great discovery might come from a telescope's lens, a quantum computer's calculation, or an equation scribbled on a napkin. One thing's certain, when it arrives, our understanding of reality won't just shift, it will transform. The universe has been playing a deeper game all along, and we're just beginning to learn the rules.